Hello guys, welcome back. This is Tanisha. So, we were actually doing the D block and F block elements chapter. In the previous video, we have covered till this part. So, let us start with the next part. In general, greater the number of valence electrons, stronger is the resultant bond. So, we have already discussed if more number of valence electrons and the unpaired electrons will be there, they will be getting delocalized. So, their bond will get stronger. Since enthalpy of atomization is an important factor in determining the standard electrode potential. Standard electrode potential is nothing but it is going to give the information how easily will the metal lose the electron and become a cation. Metals generally are electron givers, they give off the electron, and non-metals will take the electron. When you lose an electron, you get positive charge and that will be cation. So electrode potential, generally negative value it will show. So if more negative value it is giving, that means metal will easily lose electron and become a cation. So they are telling that enthalpy of atomization is an important factor to determine this. How? If enthalpy of atomization is more, that means bond is more strong, that's why more energy has to be given to break the atom's bond. So in such a case, what will happen? Electrode potential will become less negative. Less negative meaning it will not lose an electron very easily and it will not become a cation very easily. So that's why it will be noble. Noble means inert. It is not going to react very well. Why is that so? See, if metal has to react, it has to give electron. This metal is being greedy. It will say that I won't give electron. Then nobody will like to form bond. Nobody will like to be its friend, right? So that is what this is about. If enthalpy of atomization is more stronger the bond is, atom will not easily break apart. Electron also will not be given easily out. It will not form an ion easily. It will not make a bond with any other thing. So that's why it will tend to be noble. Very high enthalpy of atomization is their meaning. If low enthalpy of atomization is their meaning, the bond is weak. Easily atom is coming out. Easily you can give off the electron also. It will become a cation. This metal will not be greedy. It will be able to give the electron. So everybody will like to make friendship with it. They want to bond with it. So non-metal will come, take the electron and they will bond together. So that is what it is about. So if they want to ask question, they may be like metal A is there, it is having very high enthalpy. Metal B is there, it is having low enthalpy of atomization. Then which is more likely to be reactive, or which one will have more negative electrode potential? If they ask the one more negative electrode potential, meaning it will lose electron easily. That means low enthalpy of atomization one. So like that you can reason it out and give answer. Another thing is that generally for enthalpies of atomization or melting point and boiling point, second series and third series will be greater than the first series. You can see, right? First series is here, then second series, then third series. It is increasing. So generally why is it happening is, if you go from third series, that's 3D, then 4D, 5D, like that. So first, second, third series, if you keep on going, electrons will be more diffused, like they will be more spread out in that orbitals. If they're more spread out, they are going to overlap in a better way. We have already seen that time, right? Like how the bond is going to be between these atoms. It is solid, it is going to be tightly packed. It's just like a covalent bond, but you're calling it as interatomic metallic bond. In the previous video we have covered this part. So if you talk about like 4D series, then 5D series, 6D series, the electrons is more spreaded out. They are more spreaded out, so they can easily more delocalize. So if they're going to delocalize more, what will happen? Their bond is going to get stronger. If their bond is stronger, obviously enthalpy of atomization will also increase, melting point will also increase, because if bond is stronger, you won't be able to easily break it apart. So more energy has to be given. Then the next topic is about atomic and ionic sizes, how they are varying. So again we have studied this part also in our previous grade, saying that if you're going to go along the series horizontally, if you keep going, atomic number will be increasing and the size will be decreasing. Why is this happening? The reason is that, okay, we are talking about d block elements, electron will enter the d orbital. Now as you're going to go towards the right, from left to right along the series, atomic number is increasing. What is atomic number? It's nothing but the number of protons. So if number of protons are going to increase, number of electrons are going to increase. Proton is increasing, meaning nuclear charge will also increase. If nuclear charge is increasing, it will going to attract the electrons more towards it. And the problem is the D shell which is there, it is not very good at shielding. Shielding meaning it has to protect the outer electrons from the nuclear charge. If we have to see over here, this is the nucleus and these are the shells, for example. So if we think this is D, whichever is closer to the nucleus, that is S. So this will be B and this will be D. So whichever is closer to the nucleus, that will be able to shield better. Because it's closer to the nucleus, it won't allow the nuclear charge to come and drag the electrons towards it. Same with P. Compared to D, it is more closer to the nucleus, so it won't allow to, it will block this nucleus from trying to attract this electron. But D is actually very far from the nucleus, so it won't be able to block its power properly. So it's not able to block the power properly. What will happen? In more outermost shell, whatever electron is there, it will be easily dragged by this nucleus. So if it is going to get dragged like this, obviously it is going to get compressed. So its size will become smaller. If it's going to get, if this is going to be dragged towards the center, then this will slightly come closer to the nucleus. So what will happen? Its size is going to reduce. So that is the reasoning over here. Because atomic number is increasing, atomic number, nothing but number of protons, that will also increase. Nuclear charge will increase, more electrostatic force attraction will happen, and D subshell, which is being very far from the nucleus, is not able to shield properly, not able to block that nuclear power from dragging that electron. So that's why its size is decreasing as the atomic number is increasing. Same thing for normal atomic radius also, ionic radius also, same thing. And the variation will be gradual, not like from scandium to titanium itself some 100 picometer difference is coming. It is gradual, slowly it will be decreasing. Then one thing is said that here also generally 3D, 4D, 5D, first, second, third series, if you keep on going, there will be increase in their atomic size. Down the group, if you grow, it will be increasing. Along the series, horizontally if you go, atomic size will decrease. But down the group, if you're going to go, it will increase. So this is 3D, 4D, 5D. So more than 3D, 4D will have more atomic size. Along the series if you go, atomic size is decreasing. Down the group, it will increase. But here one thing is that if you see this graph, this is 3D, then 4D and 5D. Between 3D and 4D, if you see, there is a lot of gap. Okay, indicating that, okay, 4D is directly whatever elements are there, their size will be more than that of 3D. But if you see for 5D, they're almost same. Here they have given zirconium and hafnium, 160, 150. Only 1 picometer difference is there. They're almost equal, 4D and 5D series elements. So what is the reason for this? The reason is something called as lanthanoid contraction. 5D series, whenever we are going to write the electronic configuration for it, before that first we have to fill 4F. If you see over here, before 5D, 4F should be filled, and actually 4F is again poor shielding effect. D itself was unable to shield properly. F is coming after D, so it is not going to shield properly. Again, you can give the same reason, saying that it is not shielding properly and nuclear charge will be increasing. Shielding effect is low, meaning nuclear charge will easily be able to attract the electrons. That's why the size is decreasing. So that's why in 5D series the elements are having this 4F orbital, which is not shielding properly. Nucleus is able to attract the electrons and making it of a smaller size. So that is nothing but the lanthanoid contraction. That's why if you look at 4D and 5D series, there is no much difference between their elements size. So that's why their physical and chemical properties will also be similar. That's what they're explaining over here. Shielding of 4F electron is actually less. That's why the nuclear charge will increase and the size will decrease. One more thing to remember, along the series if you're going, radius or atomic size is decreasing. If it is decreasing, then volume is also decreasing, because size is decreasing, meaning a less space it is going to occupy. Volume will decrease, and atomic mass is still increasing only. Number of protons, electrons, everything is increasing. So if the nucleus number of protons is increasing, the mass is mostly concentrated in the nucleus. So if you go along the series, atomic number is increasing, so nucleus size will also be increasing, atomic mass increases. If mass is increasing, volume is decreasing, obviously density will increase, because density is equal to mass upon volume. So if mass increases, density increases. If volume decreases, density increases, because density and volume are inversely proportional. So that's it. Now they're asking one question saying that transition elements are going to show higher enthalpies of atomization. Why? We already learned they're having high melting points, high boiling points, and high enthalpies also. Why is that so? Because there are many unpaired electrons, because D shell is not completely filled. They will delocalize, so there will be strong metallic bond. That's why higher enthalpy of atomization is there. Next question they're asking that for zinc, enthalpy of atomization is low. Why is that so? Because if you see in zinc, unpaired electrons are not there. Zinc, everything is paired over here. 5 D meaning 5 orbitals will be there, in one maximum 2 electrons. So in one box 2 electrons can be filled, completely 10 are done. There is no unpaired electron, single one electron is not left in any box. Then in such a case, if there are no unpaired electrons, no delocalization cannot happen. There are no d electrons only available for that overlapping, for that bond making. So that's why it will become a weaker bond. So that's why low enthalpy of atomization is there. Less energy also you provide, easily the atom will come out. Now about the ionizational enthalpy. So along the series over here, ionization enthalpy is increasing. This is because as you go along the series, again number of protons is increasing, nuclear charge is increasing. That means nucleus is going to hold the electrons, it's going to attract the electrons towards itself so much that removing an electron becomes difficult. Ionization enthalpy meaning nothing but I am providing energy in order to remove an electron from the atom. So if electron is tightly bounded to that nucleus, because nuclear charge is being more, because number of protons are more, then removing the electron will become difficult. That's why whenever it's being difficult, more energy to be provided. So that's why there is increase in ionization enthalpy. Ionization enthalpy meaning how much energy to be provided. So here certain points to remember is that if you see the variation in ionization enthalpy, like along the series, it should increase. So for this transition elements, it's actually a gradual slow increase. It's not like all of a sudden dramatic change is there. Small number change is there. That is one difference with non-transition elements, because in non-transition elements it's not that much gradual, there is dramatic increase, but over here there is small increase, like if you see over here, especially for 3D, from 31 to 56, then 50 53, like that only it is increasing. So very small change, only like 20, like that it is being added over here. So that's why. And one more thing they're telling is for 3D series especially, it is a irregular trend, because it is very small amounts if you compare it with other ones also. For first ionization enthalpy of this is 3D series, first ionization enthalpy is very small values, it is only increasing. But for second and third one, it is more increasing is there, like from here to here you can see 100 is increasing. So why is that happening? If they're asking the reason, that's because actually the 3D orbital which is there, it will shield the 4s electrons, because 3D orbital will come before 4s. 4s is the outermost one. So it is going to shield, it is going to protect it from that nuclear charge. So what will happen is the size will be decreasing. That size which is decreasing is less rapidly, meaning in a gradual slow change manner it is decreasing, because it's able to shield some amount of it. Nucleus is not like dramatically fully pulling the electrons and fully the size is reduced. It's slowly as you go along the series, it's reducing. And this ionization enthalpy is actually depending upon this size. Because if size is less, then electrons and protons will be more nearby. If they're more nearby, more forces of attraction, electron will be tightly bound. You have to give more energy in order to remove it. So ionization enthalpy is dependent on this size. So because in 3D series you're able to see that 3D is able to shield that 4s, so that electrons in that 4s are not being completely attracted by the nucleus. So there is in a small change manner it is reducing. That's why ionization enthalpy, which is dependent on the size, it is also increasing only by slight amounts. It's not fully increasing like by 100 or 200 in first ionization enthalpy. Then they're taking doubly or more highly charged ions have Dn. That means Ns2, right? So doubly charged meaning plus 2, meaning 2 electrons will be gone. So S will no longer be there, only D orbital will be left. General trend of increasing value again in second ionization enthalpy, third ionization enthalpy. First ionization enthalpy meaning energy I have provided to remove one electron. In second ionization enthalpy, after removing one electron, again how much energy to provide in order to remove the other electron. Then again, if two electrons are removed, again I have to provide energy to remove one more electron. That will be third ionization enthalpy. So in first ionization enthalpy also it is increasing along the series. For second and third ionization enthalpy also it will be increasing. It will be gradually it will be increasing, but the trend will break when it comes to Mn2 plus and Fe3 plus, because it should gradually increase. The thing is that here it is increasing so much. Whenever trend breaks, meaning there is exceptionally high value or exceptionally low value. So here exceptionally high value is coming. Why is that so? For Mn2 plus, if we look at the configuration, if 2 electrons are removed, here 3d5 will be there. This is 5. So as we know, half-filled d orbital meaning more stable. If it is more stable, removing the electron becomes difficult. So dramatically it will increase so much. The steady increase should be there, but it is increasing too much. Even same thing for Fe3 plus. Here 3d6, 4s2 is there. So if 3 are removed, 2 will be removed from here. Then one more will be removed from here. Again 5, 3d5 will come. So dramatically it is so much increasing at that particular point. So trend is breaking because it should be a steady increase, but it has become exceptionally high. Then this ionization enthalpy mainly is dependent on electron and nucleus, whatever attraction is between them, then the repulsion between the electrons, and then the exchange energy. Exchange energy is nothing but when there are degenerate orbitals. Degenerate orbitals meaning same amount of energy will be there. Suppose these are my orbitals. These are my orbitals. Suppose these all are having same energy, and let me take with same spin. Electron parallel meaning same spin. Top spin only will be there. What will happen is this, any two electrons can exchange their places. This electron can come here and this electron can come here. When that happens, energy will be given out. That energy given out is exchange energy. Whenever energy is given out, this energy state will become more stable. Nature is always trying to get stable by releasing energy, because when anything is having more energy, it is unstable. Suppose if we are only having more energy, we will be keep on playing, we will be keep on roaming. But once we get tired, we sit, we sleep. That is the most stable position. So nature always wants to get stable. So if it has to get stable, it has to release the energy. It should not have extra energy. So this is one way to get stable. That is what exchange energy is about. Now exchange energy is approximately proportional to total number of possible pairs of parallel spins, meaning same spin electrons. How many will be there? That much exchange energy will come. So possible pairs, like either these two electrons can exchange, otherwise these two electrons can exchange, otherwise these two electrons can exchange. So to that, this how many pairs are there, like that it will be proportional to the exchange energy. Parallel spin meaning same spin should be there. Degenerate orbitals meaning same energy orbitals should be there. Then when several electrons occupy a set of degenerate orbitals, the lowest energy state corresponds to the maximum possible extent of single occupation of orbital and parallel spin. Now this is written in a very confusing manner, but it's nothing but Hund's law. Hund's rule says that when you're filling the electrons, So first only fill like this. After that singly occupied only, you have to start pairing them, because directly in the first box itself you cannot put off 2 electrons. If you have to fill 6 electrons, you cannot fill like this 1 2 3 4 5 6. This is a wrong method. Until unless there is this parallel spins completely covering the entire available orbitals, then only this should come. So single occupying and the parallel spins. Why is this there? This is there because whenever there is this parallel spins, same spin, degenerate orbitals, this will be almost having same energy, only all these orbitals, these will be able to exchange their positions. This cannot exchange because it's opposite. These will be able to exchange their positions, like too many are there, no, 1 2 3 4 5. They will be able to exchange and give out energy and become more stable. But if you consider this is unstable, because see here, there are too many pairs available. 1 pair is there, 2 pair is there, 3 pair is there, 4 pair is there, but here only these 3 are there with same spin, and again one more 3 are there with same spin. Also these are not filled only. So being able to exchange their position, giving out the energy, it will be comparatively less as compared to this structure. That's why this is preferable. That's why this rule is there. That's what they are telling. The extent of occupying, the loss of exchange energy will increase the stability. Now, if the stability is going to increase, ionization becomes more difficult. If it's going to be more stable, more proper, then taking out electron will be difficult. There is no loss of exchange. Okay, if D6 configuration is also there, there will be same amount of energy only lost. 6 is this. And if D5 is also there, that will also give out same amount of energy only, because the one with the parallel spins are same. 1, 2, 3, 4 and 5. So if this is D5, parallel spins are 5 in the 5. If there are 6, it's still like that. You don't have to worry about this other opposite spin. These can still exchange their energy and give the same amount of energy as D5. So there is no loss of exchange energy, meaning there is nothing like if D6 is there, there will be less energy released as compared to D5. It will be same amount only. Then this is having, Mn plus is having this configuration, and Cr plus is having this configuration. So what is happening? Both of them are having 5. So then what will happen? If it is 5, it is going to get more stable, then ionizational enthalpy will become difficult. In Mn plus, this is 5 is there, but still S is available. One unpaired electron is still available. If you're going to give enough energy, you can easily take off this electron. But for Cr plus, only D5 is there. S is not even available. And this is completely stable because it's fully half filled. So what is happening? Ionization enthalpy of Mn plus will be lower than Cr plus, because from here taking an electron is difficult. Ionization enthalpy of Cr plus will be more as compared to Mn plus. Then same thing for Fe2 plus has configuration of D6 and Mn2 plus has configuration of 5, 3D5. So again Fe2 plus will be lower, because here 5 is there, it will be more stable. You cannot easily take away the electron. Ionization enthalpy of Mn2 plus will be more. But for Fe2 plus, 6 are there. If 6 are there, there will be more repulsive forces, because in one thing 2 electrons are there. If there is repulsion, you can easily take away the electron. That is one more thing to remember. So second ionization enthalpy of Fe2 plus will also be lower. Third ionization enthalpy will also be lower for Fe. Lowest common oxidation state of these metals is +2. Now if you want to obtain any metal with +2 state in gaseous form, one thing is you need to know the first ionization enthalpy, second ionization enthalpy, because 2 electrons you are removing, and also enthalpy of atomization, because you want to obtain it in gaseous state. So you have to get the sum of them, and generally second ionization enthalpy is going to be high, especially if you take for chromium and copper. You will get D5 and D10 configuration, because NS2 NS2 will be taken out. So what will happen? D5 and D10 will be there. So then removing the electron from these full filled and half filled, if they're more stable, you will need high ionization enthalpy. So that's why second one is more dominant here. But if you consider zinc, Zinc second ionization enthalpy will be comparatively less only, because if you see the zinc configuration, after removing one electron, still one electron is there in 4s, so you can remove it easily from here. But for chromium and copper, second ionization enthalpy, after removing one electron, if you want to remove the other electron, you're only left with 5 and 10, which are more stable. So generally, third ionization enthalpy is going to be greater, because first ionization enthalpy, one electron you removed. Second ionization enthalpy, another electron also removed. Number of protons is being the same, but electrons became less. If protons are more, easily again they will be able to dominate the electron, they will be able to pull the electron towards themselves, because electrons became really less. More attraction will be there, more forces of attraction will be there, meaning electrons are again tightly bound. If they're more tightly bound, you have to give more energy to remove them. So generally, third ionization enthalpy is going to be greater. So that is why this is explaining why copper, nickel, zinc cannot, their oxidation state obtaining more than 2 is difficult. If you say for copper and zinc, getting +3 is difficult, because you have to remove the third ionization enthalpy is very high for them. Ionization and enthalpy give some guidance when you want to know the oxidation states and relative stabilities, but still it's very complex thing, so you cannot just expect some general trend to be there. So that's why we are not predicting using that mostly. Now these are the various oxidation states given over here, and the ones highlighted black is actually telling which is more stable. So the greatest number of oxidation state is generally middle of the series, like manganese, because it's having these many 1 2 3 4 5 6 oxidation states it is having. So generally towards the middle you're having more, but towards the sides you're having less number of oxidation states. Why is that so? Because in scandium, if you see the electronic configuration, 2 and 1, so there are only less number of electrons over here, so more oxidation states are not possible. Maximum 3 only will be there. What else can it give or take? And here, though more number of electrons are there, d orbital is going to have more and more electrons. They are actually approaching 10 over here, so they will be almost more stable. So they won't be giving that many oxidation states, that many electrons they cannot afford to lose, because they're mostly stable, because d orbital is almost approaching the 10 electrons, right? So that's why towards the middle only mostly greatest number of oxidation states, more number of oxidation states you can expect. So the lesser number of oxidation state towards the extreme ends, because few electrons towards the left and many d electrons might be there at the right, but again they're approaching stability, so you cannot expect more number of oxidation states over here. And scandium 2 is not possible. Why is scandium 2 not possible? It is because if you see the electronic configuration for scandium 2, why is it only +3? Because if it will lose this 3 electrons, what is this configuration? This configuration is nothing but argon. The noble gas configuration, the most stable one, it will attain. If you take away 2, this again one more electron will be left out. So that will be not much stable. That's why it is there for 3. Scandium is not having +2. Generally we are telling common oxidation state is +2, right? Almost everything is having +2. Everything is having +2 except for scandium, because it's not very stable state. That's why for scandium +2 state is not there. And then for titanium, 4 is more stable. They have highlighted 4 over here. Why did they highlight 4 over there? Why is it more stable? See, if 4 electrons are lost, again argon is coming. The most stable, the noble gas configuration will come. That's why it is stable. That's why that will be preferred. And oxidation state for zinc will be +2. So generally till manganese, if you want to get which is more stable oxidation state, one trick is that you can take s electrons and d electrons and add it off. Over here s electrons, d electrons, you're adding 3, so that is the most preferred one. 2 and 2, 4, that is the most preferred one. 3 and 2, 5, that is the most preferred one. So like that you can add the s and d electrons in order to get to know which will be the most stable oxidation state. But after that onwards, there are more in a not so predictable manner after manganese. It's not just the addition of S and D electrons. And generally, if you take other than transition elements, they will also like, mostly transition elements are the one which are having variety of oxidation state. Like one element is having so many oxidation states over here if you compare with other elements, and other elements will also have sometimes two or more than that kind of oxidation state, but it will differ by 2 units, like 2 and 4 might be there. But in transition elements it's by unit, like 1 only is the difference, 2, 3, 4. So difference is 1. So that's what they are telling here. They are differing each by unity, meaning 1. So 2, 3, 4, 5. Only 1 is the difference. Variability of oxidation state of non-transition elements, if you take any other elements and if they are having more than one oxidation state, then really they differ by the unit 2. Like if 2 is there, there will be 4. Like that. So 2 and 3 or 3 and 4, if you want to get that by one difference only, mostly you will find it in transition elements only. And there is a reason for why there are many oxidation states for transition elements itself. It is again because n minus 1d and ns, these two orbitals are having almost same energy as we have discussed in the previous video. So that's why electrons can jump from one to another. That's why electronic configuration is having many exceptions. The same reason, because they're having almost same energy, their oxidation states of losing electron from one thing and another thing is completely possible. Two shells are together as outermost, so they can lose 1 electron or 2 electron or 3 electron to make themselves stable. So that is the reason why variability of oxidation state is for transition elements. And one more thing is that d orbital again not being completely filled. If it is not completely filled, it will have free spaces, so it can again allow bonding. For there is a different sorts of bonding that can happen. So that's why its oxidation states, its valency will be too many things for just one element. Then here they are talking like one more difference between this transition and p block elements. P block elements generally, if you talk about heavier members, like if you go down the group, the size will be increasing. Their heavier elements which are there, they're generally preferring low oxidation states. Now the reason for this is, for p block actually the configuration is like this: ns and np. And if you talk about heavier elements, they generally include f also and d shell also. And we know that these both are not very good in shielding because they're very far from the nucleus. They cannot stop the nuclear charge because they're not near nucleus. They will not be able to stop the nucleus properly. So what will happen? The nucleus will grow powerful and it will be able to pull the electrons, especially from the outermost ones if they're not shielding properly. So it will be able to pull this particular ns electrons, how many ever electrons it is having, it will be able to pull that electrons towards itself. These will become less available for your reaction. So that is why inert pair meaning two are there, so pair and inert, they're not participating only because they're tightly bound to the nucleus. So only p electrons are available for such kind of bond. So that's why low oxidation state is happening. Suppose if there is configuration like this, plus 4 is possible. Losing all the 4 electrons is possible, but what is preferred? 2 is preferred, because losing these electrons is very difficult because they're tightly bound to the nucleus. Because F and D are not shielding properly, nuclear charge will attack these more if they're not able to stop the nucleus. So instead of 4, 2, lower oxidation state is preferred. This is in p block elements, but the exact opposite happens for the d block elements. D block elements, it is observed that especially from group 4 to group 10, if you're seeing chromium, molybdenum and tungsten. So generally if you see chromium 3D series, then 4D series, 5D series, these are the heavier members. Down the group if you're going, size is increasing. So these are the heavier members, meaning they have to prefer the lower oxidation state to become more stable. All of them are having 6. Our expectation is that chromium 6 only should be more stable. These should not be that much stable because they're having higher oxidation number. They should have lower oxidation number, but exact opposite happening because these are more stable than the chromium. We found out this because chromium, whenever it's in form of dichromate in acidic medium, it is strong oxidizing agent. A strong oxidizing agent basically reduced substance, it is taking electron. Whenever they're not stable, then only they will react, then only they will take electrons or give electrons. Through that we got the hint, because molybdenum or tungsten, they are not being oxidized or reduced, they are not doing anything with the electrons. That means they're already stable. If you're stable, you don't have to give or take electrons. Only if you're unstable, you will give and take electrons. So it is found out that molybdenum, tungsten, these are actually heavier members, but still with 6 as their oxidation state, they are more stable. So exact opposite is happening from the p block elements. Then low oxidation states are also possible. Ligands, as I discussed in the previous video, generally any kind of species, any compound, any ion is coming and giving a pair of electrons and making a bond with a metal, you call them as ligands. So this is actually capable of some of the ligands in kind of some complex compound, they can take the pi electrons, and also in addition to sigma bonding, meaning CO here is a ligand. It is coming towards a metal. It will give a pair of electrons to bond with it. Now nickel as a metal also will give some electrons to it, and this will accept that also. So this kind of complex compound will be formed, and in such a case oxidation state of nickel and iron is 0. So we were calculating the oxidation states like this from redox chapter generally. CO, generally it's not, any charge is not there, so you will just put 0 about it. The oxidation state will be like this, 4, and if you have to calculate the oxidation state, what we used to do, 4 into 0 plus x, because we want to find nickel's oxidation state, is equal to total oxidation state should always be 0. So 0 plus x equals 0, so x will be 0. Low oxidation state you are getting for nickel also, for iron also. So that will happen if ligand is coming and giving electrons, pair of electrons, and also accepting pi electrons and forming a complex bond. This is only possible because this ligand is actually accepting these electrons also, because otherwise if it's just giving electrons, metal will get overcrowded with the electrons. More repulsions will be there, it will be not that stable. But here it is stable enough because ligand is also taking the electron. Now here one question is given saying that name one transition element which is not showing a variable oxidation state. Okay, scandium, it is only having +3 state. But some people will write zinc. No, don't write this. This is not a transition element. It is, we are just studying about it also, but we are not considering it as transition element because it is having completely filled orbital. That's why. Then in 3D series, transition metals exhibit the largest number of oxidation state. Okay, which one? Which element? It's actually manganese. Largest number of oxidation state, it's having this many oxidation states, it is this one. And it is mainly because of the unpaired electrons available. You can see the electronic configuration over here, 5. These all are unpaired. If you draw, this is the d orbital, so one electron will be there. These all are unpaired. If it is unpaired, actually it will be easily given out. So in such a cases, it can have more number of oxidation states because they're unpaired, they can easily be given out. Metal meaning it should give out as many electrons as possible, then only more number of oxidation states will be there. That's why. So we can talk about certain questions. They might ask like this kind of question. If Cr2 plus is there and Mn2 plus is there, they might ask which will have greater ionization enthalpy. In such cases, always write the electronic configuration. If you write for Cr2 plus, it is going to be 3d4. Argon will be there. Instead of writing all the stuff, you can simply put argon. Same thing for manganese 2 plus. If you're going to write the electronic configuration, you can put argon, then 3d5. Now this is more stable due to symmetry. If it is stable, removing an electron will be difficult, so ionization enthalpy will be higher for this particular one. Now there is one more question, Cu plus and Cu2 plus. you might write the electronic configuration. For Cu plus it is going to be 3d5, and for Cu2 plus it is going to be 3d9. So in case of this, it's copper, so it's 10 actually. Yeah, in case of this, you might think that okay, here d orbital is completely filled, it will be more stable, so this will require more energy, so ionization enthalpy for this will be more. But this is an exceptional case. Generally Cu2 plus is the most stable form as compared to any other copper form. So though here 9 is there, here 10 is there, this is more stable, ionization enthalpy should be more for this, but this is an exceptional case. This will be higher for this. So like this, whenever they ask the questions, you can write the electronic configuration, but also keep in mind certain exceptions. So that's it for today, guys. We have covered till oxidation states. In the next video we can cover the next topics. So if you found my content really useful and you wanna study the further topics also, so you have to get the notification, please subscribe. And if you like this way of explanation, so please like the video. And also any sorts of feedback, any sorts of help needed, feel free to leave a comment. Thank you guys. Bye.